All right, here's a basic strengths review, some concepts, equations that are important from strengths that we will use at some point in machine design. So let's start first with stress. Sigma over A, or normal stress. So say you have a cylinder, and this is the area, and there's a force being applied up or down. Then you can find the stress, okay, which would be a Newton per meter squared, so a force per area. You also have shear stress. Let me underline stress. Tau, which is V over A, which is your force over area. And let's say you have some sort of bracket. Let me draw it out here. And you have these two pieces holding it together. All right. And so this is say like a 2x4 right here. And there's two like hangers that are attached to the wall here. So this is like a wall. And then there's a pin going through here to hold it in place. Okay, so if I draw these out, all right, there's the holes, and then here would be like the pin. Oops. Okay, this is the pin that would go between, and then you would have, let me do this in green, V, this is your shear force, okay? So if we add too much weight to it, they would shear right off, okay? Break. All right, so stress, normal stress, shear stress. Let's look at the stress strain curve. So here is sigma, and then epsilon, and then what you have is the elastic region. Then you got yielding. Then you got strain hardening up to its ultimate stress, and then you have necking. Okay, so let's kind of separate these and then write them. This is your elastic region. This is yielding. This is strain hardening. This is necking. Okay, so we're taking an object, say a pencil, and then you're pulling up and down on it, so it's stretching along the long ways. Okay, eventually it's going to break apart. Okay, this point right here, this is sigma y, that's your yield stress, and then this right here is sigma u, that's your ultimate stress. Okay, those two are very important when we deal with machine design. And then if you remember, the slope down here in the elastic is E. Okay, your modulus of elasticity. Okay, so sigma stress, and then you got strain down here on your x-axis. Now in that elastic, there's a famous equation, Hooke's law, right, which is sigma equals E times epsilon. Okay. So your modulus of elasticity times your strain. All right. Another equation that you've seen or used before is your Poisson's ratio. Nu is basically your strain of your latitude over your longitude. Okay, so if you have a cylindrical shape, okay, then this could stretch back and forth. What happened there? This way, but it could also go outward, okay? And that's Poisson's ratio. All right. You got axial load, deflection. So if you have a cylinder attached to a cylinder attached to another cylinder with different diameters, you can find the deflection at the end, and you have to use the summation of PL over AE. So P is your load, L is your length, A is your area, and E is your modulus of elasticity. You did also thermal stress equations. So delta, due to temperature changes, alpha delta T times the length. And then you got into torsion. So tau max, your torque, times C over J, which is your polar moment of inertia. And C is the outer radius of the shaft, right? Where the torque, max torque acts. And then also you'll see now, sooner or later in machine design, we can do the polar section modulus, ZP, which is J over C. Okay. So again, T is your torque, C is the outer radius of the shaft where the maximum torque is applied, J is your polar moment of inertia of the cross-section area, and ZP is your polar section modulus. And there are tables that you can use to find that equation. Okay? The last part is bending. And this is where shear and moment diagrams are very, very important. Shear and moment diagrams. Okay. And then you get the flexure formula. Sigma max equals MC over I, where M is your moment, C is your perpendicular distance from the neutral axis to a point farthest away from the neutral axis, where sigma max acts, and I is your moment of inertia. Now we can also switch this to M over S, where S is your section modulus, and you can find tables or use equations and tables in the appendices in the back of the machine design book. Okay, so if you notice, those two kind of make a simpler formula, and we use that formula like T over ZP and M over S in machine design. All right, so this is a very crude, basic concept equations that you kind of use, that you should have used in strengths, and just to kind of give you a refresher about what you covered in strengths. All right? Okay. Thank you.